Hello, welcome everyone to the database seminar on databases and blockchain and Bitcoin. Today we have an invited speaker, Arvind Arasu from Microsoft Research. He's going to talk about the connection between blockchain and databases.
So thanks, Dan, for the introduction, and also thank you for inviting me to talk about blockchains. So when compared to other speakers in this forum, I'm not a blockchain expert. I'm much more I approach this area from the point of view of databases. But as I will try to argue, the perspective of approaching blockchains from the perspective of databases is very helpful, and it gives us an opportunity to kind of like rethink some of the assumptions in blockchains from the point of view of the work that has happened in our community. I want to acknowledge a large number of people who contributed to my intuitions and thinking in this space, and most of them are from Microsoft, but we also have a few interns, including Brandon Haynes from here, who worked with us a couple of summers back. Okay, so what are blockchains? So just to start off, so a blockchain is a system that ultimately enables mutually untrusted entities to kind of execute transactions. I can, for example, so the kinds of applications people are considering for blockchains are to purchase a house and get the escrow and out of the way and so on. So if you consider, like if I want to sell a stock, right? If I go online and to a stock seller and sell a stock, before the stock sale materializes, it requires a couple of days. But ultimately, all the stock ownership is represented in some SQL database, and executing the SQL transaction required to kind of register that it went from person A to person B, it should take like milliseconds. So what explains like the multi-days to milliseconds? And it happens because often such a sale of the transaction it involves like mutually untrusted systems, and often we require like this middlemen, like auditors who need to kind of it's a very manually process. It's to kind of to verify that like no one party is cheating and so on. And the promise of blockchains is that it kind of eliminates this middleman and makes this entire process much more transparent and more efficient. So out here is a rather simplistic view of a blockchain, and almost any blockchain that you look at would not conform to this view, but it's very useful to kind of illustrate our points. So at the heart of a blockchain, you have this multiple nodes. We can view each node as this unit of untrust, in the sense that if there are three parties who are mutually untrusted, they would each run a node. And a blockchain ultimately it stores some database and it runs transactions over the database, and these transactions kind of update the state of the database. And what a blockchain will do is it runs some kind of a consensus protocol to figure out the order of the transactions, and then what happens is each node maintains a local copy of this database, and it runs each transaction locally to modify the state of this database, right? So in this case, there's a transaction. In this case, there's a sample database, which, like, let's say it has the money for Alice and Bob and so on. And if Alice transfers $20 to Bob, each node will execute this transaction to reflect the fact that Alice transferred $20. Right? Very simple. So, but the implementation, the mechanisms that are used in the blockchain now, if you look at all the existing blockchains, they cause a whole bunch of issues. Like, what are the issues? So for first, as I mentioned earlier, that each blockchain like maintains its state locally. So, and often if you look at things like Ethereum, it's kind of it's a like a main memory, the internal main memory structure, right? And so like what would happen if the scale increases? So if instead of if you have like millions of such records and so on, like a lot of issues that we knew how to handle in the database would become very relevant. So for example, you can't keep it persistent in main memory, it needs to spill to disk, and you need to build indexes, and this node can be powered off, in which case you need to like recover from such an event, you need logging, checkpointing, and whatnot, right? All these things I don't think they exist in a sophisticated manner in a blockchain like Ethereum yet, but they're essentially kind of reinventing the wheel in many of these things. So each node keeps its local state, and as this as the scale increases, we run into a whole bunch of issues. The other problem with this thing is because like oops. Other problem with this approach is that because each node has to keep a state, and And a lot of this verification properties of blockchain arises because the state is exactly like replicated on all these things. All the nodes have exactly the same state, which means that, and the idea is that when you run a transaction, everybody makes the state exactly the same state modifications. So in this case, everyone goes from Alice, balance is reflected in all of them because of the transaction from Alice to Bob. And to ensure this, it's required that any transaction has to be deterministic, which also means that we can't run stuff in parallel, because the moment you have parallelism, you have like non-determinism, which causes problems, which means that if you look at Ethereum and things like that, they run each of those smart contract instances in a deterministic manner, because they don't, basically the properties of a blockchain relies on it being deterministic, right? So which has performance implications, and from the point of view of databases, one of the work is like how do you support transactions in a parallel concurrent way, and all that work is out of the window when it comes to blockchain. And last but not the least is often these blockchain systems, they use like yet another programming language, and it's called like Solidity in Ethereum and so on. And we are moving away from the world of SQL, which has been used historically to build applications, right? So we are moving from a language which is declarative to a language which is procedural. In the case of Ethereum, it's like Solidity. So we are kind of again like undoing a lot of work that has happened in the last 30 years. So at a high level, what I want to say is data management is a pretty mature technology, and it's been around for like 30, 40 years. And at its heart, a blockchain, the application, if you look at all the blockchain applications that people are talking about, right, whether it's like managing stock data, whether it's like selling houses and so on, ultimately they're also looking at very same kind of data and transactions, but they're kind of reinventing the wheel from scratch. And it causes a lot of issues, a lot of problems, performance, state replication challenges, and also the abstractions are fundamentally different. Therefore, like building applications, like one of the things that we know internally is that it's very hard to build a blockchain application, because at the end of the day, it's not just a blockchain, right? We need a web application to access this data, like so that these users can see who owns what, and therefore they can make a bid and so on. And all these applications is much more natural to build on top of SQL as opposed to blockchain, right? So so just building a blockchain application is known to be very hard. And so the question is it required to be like this, right? So if you observe, like in this case, right, like why did these problems arise? So like why did we replicate the state and run these transactions? And this main reason for doing that is because each of these nodes is untrusted. Like node 1 doesn't trust node 2 and node 3, so they basically want to replicate whatever happened in other nodes, right? So as an experiment, like let's say what happens if we just kept a state in this node 1, right? And let's also kind of make this node 1 a standard SQL database, right? So if we do this, this is like the existing world, right? So this node 1 can run all transactions concurrently, it can be performant, we are not replicating the state is kept here, and we can use all the sophisticated things. The only problem is this node 1 can lie about what it's doing, and this node, the other nodes have to believe it, right? So is it possible to is it possible to fix this lying? So is it possible to do something about this lying by node 1? And I argue that, so what is required? So essentially this node 1 is storing all the database, it's running all the transactions, but these other nodes have to verify that this node 1 is not lying. And I argue that this is an age-old problem. So we as a community have been looking at this problem for ages, and if you look at this, so in fact we have had a huge line of work where the problem is I want to outsource the storage and computations on my database as a service. I want to run it in the cloud, but because the cloud provider is untrusted, I don't want the cloud provider to know about my information. So I want to keep all the information that I have in my database confidential. And the other problem that we have considered is I want to protect the integrity of this database. So I want to store some information. When I retrieve it later, I want to be confident that I do get what I stored. So in fact, this work, like I've just illustrated one paper in this work, which won the Sigmod Test of Time award, but there's been a whole bunch of work here. So I argue that basically I'm arguing that we can kind of leverage this body of work to kind of like revisit blockchains and kind of improve their performance, abstractions, and so on. So, so this is a high level thing. So, okay, so assuming we want to use this work, is it a solved problem? So is it just a question of just blindly using all this work and then just putting them in a blockchain? So I think there are a lot of like subtleties. I won't go into all of the subtleties today, but what I thought is like at a high level, what's happening in this body of work is that people have focused mostly on the publication part of it. So they want to publish something in the cloud, and they want to like verify when they access this data, like whether like what you accessed is what you published. So like one of the important things for blockchains is the update thing, right? We ultimately in a blockchain we want to run, we want to update the state of the blockchain. We want to run transactions, but a lot of the work in this body has not focused on updates and transactions. So and we have basically performance issues when it comes to updates and transactions. Dan?
Did they even consider integrity? I thought they only consider confidentiality.
Right. In this paper, they focus on confidentiality, but they also kind of look into integrity. But this is just like, I just highlighted this paper because this won the Test of Time award. But there's been a lot of work that focus on integrity. And the entire, like as I'll talk, like people have looked into Merkle hash trees, and there's this whole bunch of other techniques that people have thought about here, which are all kind of relevant. So at a high level, what I'm trying to say is that, like if you look at blockchains, the only way they're doing that is everyone just recomputes to verify. So if you store some transaction, some state, if I have some state, and if you both run a transaction, because we don't trust each other, each of us kind of recomputes the work to verify it. So, but what I'm saying is, if the work is represented as like SQL, we don't have to recompute. We can basically, you have mechanisms where without recomputing, I can verify that your computation is correct. So, and all that thing is relevant to blockchains is what I'm trying to say. Okay, so like what I'll do in the rest of the talk is focus on one work, which is mostly work that we did, and on how to solve this problem, because I want to kind of illustrate some of the issues, some of the challenges, and so on. So like what we'll do is we'll kind of simplify the problem. So assume that we want to store on the cloud a simple key value store, which means that the operation that I do is I just want to put a key and a value and retrieve the value for a key. This is the only operation that we want, but we don't want an adversary who is modifying the integrity of the database in the cloud. Therefore, what we want to do is we want to support a verify function which can be run at any of these clients. And the meaning of this verify function is that we would modify the protocols. We would basically, instead of just putting and getting values, we would add additional information onto this interface, such that if everything is running properly, this verify function, when it's run at these things, would return true. And but if you have an adversary who is modifying the state, this verify function would return false. So we want to come up with this functionality. So if this happens, the verify function would return false, and we'll know that this provider is cheating. So if we just return back to our earlier picture on the blockchain, so what we can do is we can just have this node. It can do all the function, all the computation. The other nodes can just run a verify function to make sure that this node is not doing something wrong. So that is a high level idea. Okay, so we'll also kind of, because we are interested in running transactions in a concurrent way, we'll try and understand what it means for verify to return true. So we'll build a system in such a way that if verify returns true, like we have like sequential consistency of all the transactions. So it's like you just look at all the transactions issued by all these clients. We'll just linearize all these transactions, and the effect of each transaction is consistent with some linear ordering of all the transactions. And the system will, if you should ensure that each operation, like an adversary cannot introduce an operation, and an adversary cannot like replay an operation. So each operation is from a legitimate client, and it happens only once. So we want to build a system of this nature. And sorry.
Yeah, this is our next slide. So when are you imagining like a multi-tenant database or just a single user?
Right. So in this case, I'm kind of moved away from the blockchains world. So we'll just study this problem and then we'll come back and see how it. So in this case, what I'm doing is I'm running some key value store in the cloud, and I have like multiple clients who are issuing transactions to the key value store, and I want the property that if this verify return, and in addition, I want to support a verify function at each client to verify that this key value store is running properly. It's not there's not an adversary who is kind of tampering the state of the key value store, and I'm trying to formalize what it means to verify when there are multiple concurrent transactions. So this is.
I think it's possible you have like you can define like there exists order of the transaction.
Right.
But does the client like have some notion of the previous state of his or her own transaction will be run? Like because is there any dependency on the state?
So if I'm one of the clients, and if I run some transaction and I receive a commit from the database, and if I run a subsequent transaction, then it is known that this ordering is consistent with my local ordering. So the subsequent transaction that I issue would happen after this transaction. So it is locally consistent in your ordering, but it's also linearizable in a global sense. The transactions of all the clients would be ordered in some way, right? So this is a property that we want.
And then the proof that you provide to the user is that if the user can the user get some sort of like a verified guarantee such that when I issue this transaction, and the global state of the database will be like sort of moved to the next state as if I'm only the one issuing the transaction.
How can that be? Because there are others issuing. The transactions that I issue would see the updates of other clients also, right?
I think that's what I mean locally consistent.
Yeah, it is guaranteed to be after my previous transaction, but there are no guarantees. If he submits a transaction, the system can arbitrarily order my transaction with respect to his transaction.
I'm thinking the case that there could be some dependency, but please go on.
Yeah, there could be dependencies, but it's at the end of the day that as long as it's linearized in some way, it's fine. Yeah, we can talk offline if we're. Okay, so we want to provide all these guarantees in terms of an adversary who is all powerful, who controls the entire cloud. He can install software. He can run completely different bits on the servers in the cloud. The adversary controls the OS, memory, whatnot, right? So we want to provide these guarantees with respect to such a strong adversary. And in fact, one interesting property is if you build such a system, it also is a catch-all for unanticipated errors. If there are bugs in software or hardware failures, it will automatically come up as an verification failure in a system, right? So in this case, what we'll do is like for this talk, I'm going to assume like we have some kind of a secure hardware on the cloud servers, and basically the way to think about the secure hardware is it's like some platform which the adversary cannot modify. So you can keep a small amount of state inside the secure hardware, and we can do a small amount of computation inside the secure hardware, but the adversary would not be able to modify what's happening here. But any such state is not persistent in the sense that the adversary can kind of, well, like modulo a small amount of counter, the adversary can like reboot the secure hardware. He can power off the secure hardware, but when it is running, the adversary cannot modify the functionality of the secure hardware. Secure hardware is like strictly not necessary. We can basically get rid of secure hardware and get everything that I'll be talking about. It is valid without the secure hardware, but it just makes it easier to present ideas with secure hardware. So this is strictly not necessary. Okay, so how do we build such a system? So we want to build a system where we store a key value store in the cloud, and we want to protect it against an adversary that we talked about. So we'll start off with an approach which is not correct, and then we'll kind of build on it, right? So the first approach is what we do is with every record we attach a signature, and the property of a signature is that it basically protects the message of its payload. So in this case, what I'll do is we will basically say Alice has a balance of 100, and we'll sign it to represent that fact. And what happens is that when I retrieve a record, so suppose I want to fetch the balance for Bob, along with this output that Bob has a balance of 50, I'll include the signature, and this verification procedure is basically verifying the signature. So a very simple approach, and if the adversary, for example, modifies the balance to some other value, the verification would in fact find it, because the signature is protecting the value. The signature of Bob and 0 would not be the signature for Bob and 50 by the construction of signatures, and the verification would find this fact. Like, let's assume that there is one secret key. This anyway, just we are not going to use this mechanism, so just a high level idea. And so in this case, every record that is retrieved is authentic. You can't force this like signature. So any record that you retrieve is authentic, but it can be incomplete in the sense that I can basically say that I don't have a record for Bob, and there's no way for me to verify this fact. And I can also do something like, I can do this replay attack in the sense that assume that I have this balance for, initially this balance for Bob was 50, therefore I stored a signature for 50 and Bob, and then I updated the value for Bob to 60, and then I stored the signature for Bob and 60. What the adversary can do is, when I retrieve the record for Bob, the adversary can just remember the old signature and return the old signature, right? And in this case, although Bob's record was updated to 60, I can't find it, and if I just verify the signature, I believe it's a correct record. So the problem with that is basically it's I don't have any freshness guarantees, right? So ideally, I want a system that provides authenticity, completeness, and freshness. And in fact, you can show that any system that has all these properties is equivalent to the properties that I mentioned earlier, like this linearizability property. These are two equivalent views of the same guarantees. Okay, so how do we do this? So in fact, there's one like very well-known approach, and it relies on Merkle trees. And this Merkle tree is a very useful structure that appears again and again in this verification systems. In fact, Bitcoin, Ethereum also use Merkle trees. I don't know if you guys talked about it. So how can we solve the problem with Merkle trees? So the idea is that, so in this case, I'm just moving from Alice, Bob to some like much more abstract values just for illustrative purposes. So suppose I want to store all this. In this case, the first field is the key and the second field is a value. Suppose I want to store it. So what I'll do is I'll start off with a regular like search tree structure on this thing. So this is a regular like a binary search tree that indexes these keys and values, right? And what I'll do is with every pointer, I also store the hash of whatever is pointed to. So in this case, I have a pointer to this node, and along with the pointer, I'm keeping a hash, and this is a standard SHA hash and so on. And the property of the hash is that what this means is that it basically it's not possible to modify the contents of this node without affecting the hash. So if I modify this record, the hash will change, right? So and I just keep for along with every node, I'm keeping the hash. So in this case, in the root, I'm keeping the hash of the next node and so on. And ultimately, the hash of the node of the root is stored inside the secure hardware. And now, suppose I want to look up a value. Like what the system would do is it will basically like walk down the structure onto the leaf, and then it will basically pass all this path onto the secure hardware. So in this case, suppose I want to get value 3, I'll just walk down from the root until I find this value, until I find this key, and I'll forward to the secure hardware this entire path, right? And in this case, what happens is because the hash of the root is kept inside the secure hardware can compute the hash of this node, and if it matches the hash that's kept inside, I know that this root that was forwarded to the secure hardware is indeed correct. And because this root contains a hash of this node 4, and if this hash of the node 4 matches the hash that it is computed inside the secure hardware of this node, it means that this node is in fact correct. It's not been modified, and recursively so on forth. So essentially, what this means is using the hash of the root, I can find out if every value in this path is indeed valid. And at this point, I know that the value that is stored in the leaf is valid. Therefore, the V3 that I stored for this thing is indeed valid and up to date, and I can return that to this client. So, and because I don't want, so essentially what the secure hardware would do is it will basically output the result as V3, and it will basically contain a signature indicating that V3 is in fact the right value. So this is, so yeah, you can work out the other details for other operations, but using Merkle trees we can provide a solution that is complete, that is authentic. It has all the properties that we want, right? So okay, so and this verification is basically verifying the signature. All the work is done in secure hardware, and as I mentioned earlier, we can move all the work in hardware onto this client, and secure hardware is strictly not necessary. So what's the problem with Merkle trees? So is Merkle trees the end of the thing? So one of the problems with Merkle tree is that, so like one of the problems with Merkle tree is that it has a lot of issues with concurrency. So every node is basically reading the root because it needs to pass to the root, and every time I update a node, I have to modify the root. So in this case, I assume that I'm updating this V7 for this K7. I have to basically modify this node, which means that I modify this hash, which means that I modified this node, which means that I need to modify this hash, and ultimately I need to modify the hash of the root. So every modification, it affects the root and the hash that's stored, and every lookup needs to like read the root. So which means that there's a read-write conflict at the root, which means that I have a lot of concurrency issues. So in fact, we did this, and we kind of like built a Merkle tree and looked at how much concurrency, how much performance we can get with concurrency if there is a lot of updates to this database, and we kind of maxed out at something like a few tens of thousands key value operations per second, right? Which is like a few orders of magnitude slower than the state of the art, like main memory index structures.
So how much faster would this be if the hash value of the root is stored not by the secured hardware, but is stored as a client?
Yeah, it will be much slower, right? So in fact, the paper that uses, it's like there's, I think so the last paper that used to store the hash of the root, not in secure hardware, but at one of the client nodes, it reports transaction rates of 100 transactions a second or so. So it's really, really slow.
That key needs to be shipped around globally.
Yeah. So it's.
Let me rephrase the question. What happens if you forget security and would store this key explicitly as a server in the regular maintenance?
Then why do you need to keep the hash, right? If you forget security, then you can just build a regular data.
I'm just trying to get a sense, where does this slowdown come from?
Oh no, if even without secure hardware, if you just kept it in server, you didn't go to the secure hardware, avoided the cost of going to secure hardware, you would still be at this rate. Because this is not limited by the secure hardware latency. What's happening here is that every update is basically taking a lock on the root, and it's precluding other transactions from proceeding. So it's as if like you just had one node and you're kind of changing that. So while if we didn't have this artificial concurrency bottleneck, you'd be able to much faster. If I'm hitting like random keys in the database, there won't be any concurrency issues. I would just go in parallel. So that's the problem, right? So in fact, we will address that problem. So how can we solve it?
From the security point of view, what kind of the threatening model is deal with? So for example, if I'm a user of this key value store, right? So when I update a value to the key value store, do I get a Merkle tree root that?
Right. So in this case, I'm kind of offloading all the work to secure hardware. So secure hardware is my proxy to verify that fact. So, but as I said, you can move away from secure hardware, and I can keep a hash locally.
The security hardware is kind of have to be trusted.
Yes.
The user have to trust the security.
So secure hardware in this, whatever I'm presenting, secure hardware is part of the trusted computing base. So if secure hardware is gone, all guarantees are off. But you can, as I said, you can get rid of secure hardware and keep things locally. So that is, it's not required, but so in this presentation, I'm just assuming secure hardware.
You restart the machine, then the secure hardware.
Right. So that's why I kind of withhold myself earlier, right? So the secure hardware needs, so in any of the system, whether you need to keep some state that is protected such reboots. So you can get by with secure hardware which just keeps a counter that basically remembers how many transactions or so on, but that counter has to be persistent. If you assume in these systems that secure hardware has no state and I'm not keeping any hash at any of these clients, so essentially what that means is the adversary can just like revert the state to the initial state, and there's no trusted state to verify that has happened. So this is not possible to provide any such guarantees. So we need at least one secure, one persistent counter in secure hardware.
That's normal, right? Most of those chips come with NVRAM for those.
Right. So if you look at the things like I think FPGAs. So I think when people talk about secure hardware, there are a couple of technologies that come to mind. One is Intel SGX. Intel SGX has some story for such persistent counter, but that's like some people say it exists and others say it's not secure. So I don't know. So but FPGAs, like we can certainly like construct FPGAs with non-volatile storage.
I think we're like kind of, at least I think a bigger question is that because this is like as a model of cloud service, right? And it's closed source, and user didn't see at the actual implementation of the system, right?
Oh no. So that is easy to address, right? So the way I would do something like that is, in fact, we do that for always encrypted also, right? It relies on always encrypted is a SQL Server offering where you'll be basically using secure hardware to do some computations on encrypted data. And again, your question is relevant, right? How do I know what is running inside secure hardware is correct? So the way I would address that problem is I would basically publish open source the code that's running inside secure hardware, and any secure hardware would allow what is called as an attestation protocol. You can basically essentially what it means is the platform itself would compute the hash of the binary that's running inside secure hardware, and as part of like setting up a secure channel with that with the secure hardware, it will publish that hey, this binary that's running inside secure hardware has a hash SHA hash of 1234, and you can basically you can also compute the SHA hash from the open source version and verify whether these are the same. So I can verify the binary that's running in secure hardware is what I want it to be. So we can prevent it against such attacks. And it's kind of necessary for any use of secure hardware. So okay, so in this, so like what I'll talk about is one of the systems that we built. It's called Concerto, that kind of avoids like some of the problems of Merkle trees, and it achieves like it basically achieves millions of transactions per second, and it avoids some of the bottlenecks of Merkle trees. So how do we do that? So until now, when I spoke about verification, I was implicitly talking about online verification. And the online verification, the model is that I'm accessing some, I'm doing some operation, I'm looking up some operation, and I'm verifying the integrity of the data before I am accessing this data. So suppose I'm looking up a value or a key, I'll verify that the value is indeed correct before I return. Right, so it's the most natural verification model, and it's called online verification, right? So with every operation, I will return a result, and if I verify and if verification passes, I know this result is valid. So, and in fact, we can show that online verification would imply some of the bottlenecks of Merkle. So in fact, there has been formal work that shows that if you want to be in the world of online verification, you can't avoid this logarithmic work. It is necessary. You have this papers that show that, right? So like what we'll do is we'll kind of move away from online verification and go to a verification model that is slightly different, but it allows us to get a lot of performance benefits. So in this verification model, what we'll do is like when I request an operation, when I do an operation, I'll get some kind of a signature from the trusted module that will basically not verify the operation for you. It will basically record something in its internal state, and it will basically sign something like I have witnessed this operation and its result, right? But it's not like it's possible that this result of this operation is incorrect, but I won't find this immediately. So Alice can submit an operation, Bob can submit an operation, each of them obtains a signature, and a signature is basically a future guarantee that if the output was in fact not correct, I can run an operation later and verify that it is in fact correct or not, right? So essentially what's happening is Alice submits work, Bob submits work, and like hundreds of other people submit work. And this work is kind of recorded in the secure hardware, but no verification happens. Like later, Charlie can come and say, I want to verify all the 100 transactions that happened before, and the system would verify that for you, and it will return whether all the 100 prior operations were correct or there was one operation which was incorrect.
What's the purposes of these temporary signatures?
Basically, otherwise, how do I know that? Otherwise, it's possible that the system is lying about the output, and it's not. Essentially, what's happening is any computation, any output of the system has to be routed onto the secure hardware, because ultimately secure hardware is the one who's going to verify the final thing. And for Alice and Bob, I need guarantee that the secure hardware has witnessed my operation. Otherwise, if the secure hardware never witnesses my operation, then I would not know that some future the verification would actually involve my operation, right? So it is necessary for you to have some output from the secure hardware. Otherwise, this guarantee is right. Magda?
So does this mean you have to have this long log of now all the witnesses, kind of everything that the system has witnessed? Because there could be a very large number of reads, and is this not going to grow with the size of that?
No, this like it's not. I don't think we maintain a log anywhere. It's just all these facts are written to this client. I don't. The system doesn't keep a log of all these things anywhere. You can.
You have to somehow go back to verify all the previous.
Yeah, but we'll do the verification without keeping the log. The verification, it's as if it kept a log, but what is kept is just a small hash value. So that's the interesting thing. Yeah, so if, as I mentioned, if any of the earlier operations was incorrect, this verification would fail. It's almost like a batching verification. Instead of verifying every operation, I just batch 100,000 operations and verify them in one go. And often, as in computer science, with this batching gives us a lot of benefits.
Completeness property you talked about, because in some sense, if let's say Alice issues an operation, it's a result back, but finally you're saying it could not be as part of the database.
Right. Yes.
But how
The verification would fail, right? No. Are you saying that is?
No, you said some operations might succeed and some operations might fail.
No, there is one thing of operation success. So suppose I try to insert a key which is already there, that operation might fail for legitimate reasons, and that is okay, right? What is not okay is I try to look up a key and the system says it doesn't exist when it in fact existed. That is not okay, and that would still be caught by the system. So in terms of this end-to-end guarantees, nothing changes. It's the same guarantees. But instead of getting a verification output at every operation, you get it at the end of like n operations. So that's the only thing. Otherwise, nothing changes.
Like numbers of operations differ.
Well, it's a completely configurable thing. So we can do it every operation, in which case it becomes online. If you do it every 10 operations, every 100 operations, it's completely configurable.
Just we can get the time to it.
Yeah. So yeah, there are a lot of. Okay. So until now, I spoke about online integrity, and online integrity is I'm checking the integrity before as each operation is computed, and the integrity model that we'll use in Concerto is a deferred integrity. And as an example, we'll check every X minutes. I'll check the integrity of all the operations in the previous X minutes, and so on. And as we'll see, it gets us like significant performance benefits. Okay, so how do we do this? So what I'll do is I'll kind of outline how we do it, and the way I will do that is I will reduce key value integrity to what I call as memory integrity. Like, what is memory? Memory is, like locations and addresses, and it's a much more simpler abstraction than key values, but you can reduce this problem to that problem. And we'll use a pretty old paper on memory integrity, and this is a paper by like Manuel Blum and others to solve memory integrity. And we will use this verification, the flexible verification model that we introduced to solve memory integrity. So this is what we'll do, right? Okay, so in fact, like maybe I talked about memory integrity. So this is memory integrity. What's the memory integrity problem? So I have a bunch of memory locations, and these memory locations have addresses, and I'm performing like reads and writes of memory. So assume there's some untrusted memory, and I'm performing reads and writes of the untrusted memory, and I'm a trusted machine, and I'm witnessing these operations of memory operations. And I need to figure out if these memory operations are in fact valid, in the sense that every read that I do to a memory location, it corresponds to the last write of the memory location, right? If this property is not valid, I will have to flag it as incorrect memory operation. Otherwise, I will say it's a correct memory operation, right? So this is almost like key value integrity, but this is memory integrity. This is much more, right? Okay, so suppose we have a solution for this memory integrity, and how can we build a solution for key value integrity using memory integrity? So what I'll do is I'll organize memory as follows. So this is memory which is protected using memory integrity, and I will every location of memory I'll basically split into this 3 tuple. And what I'll do is so suppose I want to store. So this is the state of the key value store, right? And what I'll do is in arbitrary location of this memory, I'll keep ranges of these keys. So one range is -infinity to 2 is a range, and another range is 2 to 3, and another range is 3 to 5, and 5 to 7, and 7 to infinity. I'll just keep all the ranges. So basically there are n keys, there are n plus 1 ranges, and then I also store the values in the other field, like whenever they're relevant. And I argue that what happens is, so suppose I want to look up a particular value, and suppose we had like for now, let's assume that we have a solution for memory integrity, right? And if so suppose I want to look up a value, what I'll do is, what the untrusted system will do is, it will basically forward like one cell which contains the range. Suppose I'm looking up 3, so this range is contained in this interval, so it will forward this cell, this memory location, to the trusted hardware. And the trusted hardware is basically doing memory integrity, so it knows that every location in this memory is correct, and it knows that this invariant, that every interval in the key interval is kept in this memory. So it knows that we have this interval, and it knows that V3 is the value associated with this key. Therefore, it knows that V3 is the right value for this key. So it can answer that. So suppose I do a lookup for 4. Again, this untrusted machine would forward the same interval with V3, but now the trusted machine, the secure hardware, has enough information to know that the value 4 is not in this database because I see an interval, right? So it knows that it can return to the client the value 4 is not present, and that would be a correct value. So if we can somehow magically solve the memory integrity problem, we can solve the key value integrity. And as an example, so suppose of an update to this memory, so suppose I insert a value 4. So what I'll do is the untrusted machine would forward the interval which contains 4, and it will also forward an empty memory location. It could be any of the empty memory locations. In this case, it will forward 5. And what this memory would do is, it will basically and what this secure hardware would do is, it will basically modify this memory to kind of reflect this invariant that we are maintaining. So it will return 4, 5 with V4, and 3, 4 with V3. So at every given point, the secure hardware is basically it's involved in maintaining the invariant that every interval is basically kept in memory, so on. So yes, it's kind of it's the same idea, right? So okay, so essentially that's basically the thing, right? So that's how we do it. So we just use memory integrity, and we store in this special memory that's protected using memory integrity all these ranges, and we build a regular key value, an index structure over all the keys. So and to basically essentially and this structure is required because I need to identify this memory location that contains the range, and for that I just build a regular index. So the advantage of this entire solution is this indexing is not required for any of the security properties. It's not relevant for correctness. It's a pure performance accelerator, and we can use any index structure to kind of index the state. So unlike this Merkle tree approach that I talked about, where the index structure is part of the trusted computing base, it's involved in ensuring the security properties. So now the index structure is completely outside the security. Okay, so the important thing is how do we do this memory integrity, right? And as I mentioned, this memory integrity that we kind of revive an old paper by Blum et al. And then the paper is called Checking Correctness of Memories. And I'll basically mention the high level ideas, and then we'll get it. So the idea is that if a memory is working properly, right? So I'll write something and I'll read something. I'll write something and I'll read something. So every time I read, it will correspond to one of my earlier writes. So if it's somehow magically inside the secure hardware, it is witnessing all the reads and writes, I'll keep all the write set and all the read set. So this write set should be equivalent to the read set, right? So this is a high level property. So but initially, like let's assume that I just wrote the initial version of all memory, so without reading. So I wrote H for location 0, E for location 1, L for location 2, and up to so on. So initially this write set will contain like 0, H, 1, E, 2, L, and so on, right? So one for every location. And then suppose I do a read. I read H and I write C. And essentially what I'll do is I'll add to the read set what I read, and I'll add to the write set what I wrote. The invariant is that at any given point, the write set will have exactly 7 more entries than the read set. And 7 because that's the, or 8 more entries, 8 because it's the size of the memory.
So you're reading from location 0 and you should get back H.
When I'm writing to location 0, a new value C.
You're writing a new location, okay.
So I read 0, H and I wrote 0, C.
What happens if I just want to read repeatedly from location 0?
Like for now, let's not worry about repeated reads. Let's assume that every read is distinct and every write is distinct.
So after every read there is an immediate write?
Yes.
Okay.
So for now, we'll fix that problem. So and then I read some other location 4, and I read a value 0 and write a value x, so on, right? So I just keep doing it. The interesting thing is this read set is a subset of write set. And if I just eliminate everything in the read set from the write set, what is left is the last version of the updated version of all the write set. So this way this Blum like memory verification works is that at every given point it keeps the read set and write set inside the trusted hardware, and when it needs to verify, it will scan the entire memory and update its read set alone and without updating the write set. And then if everything works correctly, that this read set should be equal to write set. And as you rightly pointed out, this scheme will break if I read something without writing. And what this Blum technique will do is it adds another field, hidden field, that basically means that that contains a timestamp that makes every write unique. And even if when you read without writing, you just write back the timestamp. Therefore, you are writing some unique values every time. With that modification, you do have this property. No, you cannot. You have to read and write. Yeah. Okay, so this is I talked about verification scan, but of course the trusted machine cannot keep a log of all the reads and writes. The interesting thing is you can construct a hash function that basically approximates the set. Instead of keeping the log of all the reads and writes, you can keep a log of you can keep a hash of the read set and the write set that has the property that if the read set ultimately after verification, if the read set and write set are identical, the hashes would match. If they're not identical, the hashes would not match. But much more interestingly, the hash has the property that updating hash is basically a very simple XOR after doing an AES operation. So when you read and write, you'll read memory. You'll basically pass it through an AES block. AES is a encryption mechanism, and then you'll XOR the output. This is all you do. It's a very simple operation. And this is essentially for every memory like read and write would just involve one XOR and one AES operation. And this properties that I mentioned would still valid. So it's extremely efficient. There's no bottlenecks. You can read in parallel any number of memories, and every read is basically an XOR. And that's all you do. So there are no this memory verification introduces no bottlenecks anywhere in the system. So in this case, I have a bunch of other implementation details that we can basically skip over. So I'll just mention the high level idea. So the original Plum paper, it introduced this memory verification is called offline memory verification. It's an abstract idea. So the abstract idea is that I do all memory operations, and then offline, after all the operations, I kind of read back memory and verify it as correct. So what we did is we kind of like made it like repeating. So you can do this deferred verification any number of times, and it's not offline. And the way we do it is what we call as epochs. So we just split the memory operations into epochs, and in every epoch you do some operations and you do some checking. You do some operations, you do checking. So we modified the Blum algorithm to kind of work in a
that you need to see the entire memory and check that your hash function is
right. So which is why it goes back to our original guarantee, right? We want to do the entire batched checking.
Right, but what worries me is that if you compare this with Merkle trees, Merkle tree checking means just checking a pass of
log thing, right? So yeah,
it's much cheaper on for a Merkle tree.
But it's only for you're right. So this mechanism would have value if you do some order m, if m is the size of memory, if you do order m operations before checking, so every operation the amount of work is order 1 amortized.
The amount of this is essentially your interval at which you're checking.
So if it is much smaller than memory, if you do verification at much smaller than the memory size, then it's not obvious that you do better than Merkle. But independent of that, you don't have any of the concurrency bottlenecks of Merkle, no matter what, and that is very helpful as well. So this is one idea. So this is putting it all together, right? So when you do a lookup, we walk through the index, we access that memory. Suppose I'm doing lookup of 6, I walk an index, I identify this location, and then I forward that location to the secure hardware, and the secure hardware would do an XOR to update the read set, write set, and then it will basically update the XOR to kind of update the write set, and then it will respond to this client. So this is basically it. And when I want to verify, I'll scan this memory, and then I'll go to secure hardware, and that will use memory verification to kind of check this thing. So this is the basic idea. So I can skip over all the performance optimizations. So one thing I didn't mention is all this thing, what runs inside secure hardware. It kind of goes back to a question. It is extremely small. So all that needs to do inside secure hardware is I need to basically have an XOR. I need to have AES. So whenever I read something, I do an AES, I do an XOR that updates the read set and write set, and I do one comparison to verify that this looked up is like whatever key you're accessing is within the range of the cell, and that's it. So our implementation is like less than 100 lines of code, and our trusted computing base is essentially 100 lines of code, and everything else is untrusted code that stays outside. In fact, we implemented this inside FPGA, and it's like so simple that we could hardware optimize it, implement inside FPGA, and we get performance like we are within factor 2 of the state of the art key value store, which doesn't provide any integrity. So we can approach performance. We are comparable to the state of the art key value stores, as opposed to Merkle trees, which have an overhead of 2 or 3 orders of magnitude. So that's basically it. So I talked mostly about a system called Concerto, which is a key value store with formal integrity guarantees, a small TCB, high performance within factor 2, and the other thing is like software engineering costs. Like the only thing that was required is we are using an index, unmodified index. So we just could kind of, in terms of software engineering, you just take an index, we just modify what is stored at every level. So it's like 100 lines of code modification, but still we managed to get performance with integrity guarantees comparable to that. And as I mentioned earlier, like I believe that a lot of these techniques are kind of relevant. We can kind of implement these techniques inside blockchains and kind of relevant, and we are actively working on this currently. Okay, thank you.
for one question. So maybe my question is, so what needs to happen if I don't have a secure coprocessor in my server?
Oh yeah, so let me take this off. Oh, this is recording? Oh, okay. So essentially what's happening is if there is no secure hardware, we can still kind of, so what is kept in secure hardware is just hash, the read set hash and the write set hash. You could still kind of simulate the actions of secure hardware by keeping those hashes of the server at the client.
Distributively or
Right.
somehow.
Right.
Can you not emulate the secure hardware in the VM?
We could. There are already technologies that do that. But again, the problem with that is anytime you introduce secure hardware, it is kind of a non-trivial assumption. And initially, when we did this work, we lived with that assumption. But off late, we have kind of moved away from secure hardware. We're trying to kind of build systems without secure hardware. And in this case, we can build systems without secure hardware.
Okay, that's all the time we have. Thanks, Arvind.
Thank you.